Okay, so on this video I just have several examples of writing radicals in the simplest form. In other words, simplifying them. So square root of 18. I look at that and I think, are there any factors of 18 that are perfect squares? Because it's a square root, so I need perfect squares. And there's a 9. So I factor it as 2 times 9. The square root of 2 part won't simplify, but the square root of 9 part will. Okay, because the 9 is a perfect square. Okay, and then you can split them apart, right? Because we have a rule that says you can do that. And then the square root of 9 is 3. And we usually write that in front so that it looks like it's a coefficient of the square root of 2. The other reason we do that is because sometimes if you write the 3 behind the square root of 2, people will extend that bar over the 2 too far until it's over the 3. And then they'll end up thinking the 3 is inside the square root, which it's not. Okay, so we put it in front usually. Okay, square root of 121 over 9. That's the same as the square root of 121 over the square root of 9. And those are both perfect squares, which is nice. So remember, 121 is 11 squared. It's one that you're supposed to have memorized. So that's 11 over 3. Next one, square root of 64, x to the 8th. 64 is 8 times 8, so that's 8 squared. And x to the 4th is x to the 8th is x to the 4th squared. So they're both perfect squares. Right, that's x to the 4th squared. So the square root of 64 is 8. The square root of x to the 8th is x to the 4th. And notice when you go from here with the square root, it's an index 2, square root, you're actually taking half of the power of this variable. So that's x to the 4th. It always works that way. Cube root, you'll take a third of the power. Of course, then you'd want a multiple of 3 here. Fourth root, you'll take a fourth of the power. Like the 4th root of x to the 8th would be x squared. It always works like that. It's kind of a good thing to know. We'll talk more about that in a later section. Okay, square root of 5 times x to the 5th. X to the 5th is not a perfect square, but we can peel off a perfect square factor from there. So x to the 4th. So x to the 5th is x times x to the 4th. And index 2 divides 4. So that means it's a perfect square. X to the 4th is. And so that part simplifies. Right? So I separate the part that simplifies out. So I have the square root of 5x times the square root of x to the 4th. And the square root of x to the 4th just becomes x squared. And I just wrote it in front. Kind of like I did with the number 1 here. Wrote the 3 in front. Here I just wrote the x squared in front. Don't have to, but I did. It's just more common. Okay, cube root. So this is our first cube root one. So I need perfect cubes inside in order to simplify. And negative 1 is a perfect cube. It's negative 1 times negative 1 times negative 1. Right? And so... right? So it's negative 1 cubed. Cube root of negative 1 cubed. And so that's just going to be negative 1. We use a lot for when there's odd indices, like cube root, 5th root, 7th root, 9th root. They'll work the same way with negative 1. 5th root of negative 1 is negative 1. Okay, and we use this whenever we have a cube root or a 5th root or a 7th root of a negative number. So cube root of negative 8, you can look at it as cube root of negative 1 times 8, which is the cube root of negative 1 times the cube root of 8, which is negative 1 times 2, which is negative 2. Now, we don't usually go through all these steps, because notice a cube root of a negative number will be a negative number. So all you have to do really as a shortcut is just take this negative, and a cube root, you can take the negative inside and just pull it out. Same thing with a 5th root, 7th root, 9th root. Any odd index, you can just take the negative and pull it out. You can't do that with a square root or a 4th root or something. Just the odd indices. Okay. So yeah, so cube root of negative 8 equals negative the cube root of 8, which simplifies to negative 2, of course. But that's the point I'm making there under this bracket, is that the negative just comes out when it's a cube root, right? Okay, next example, square root of 60a cubed over 7, or c to the 7th. Now, this is a square root, so the index is 2. 60 is not a perfect square. A cubed is not a perfect square. C to the 7th is not a perfect square. So I try to factor out of these things that are perfect squares, if possible. If not possible, it doesn't simplify. So 60 is 4 times 15. 4 is a perfect square. A cubed is a times a squared. And a squared is a perfect square. And c to the 7th is c times c to the 6th. C to the 6th is a perfect square. So you're factoring it so that the, for square roots, you're factoring this so that the one factor has an even power, because those are perfect squares. So I just split the numerator and denominator, did the square root separately, and I put the perfect squares together just because I felt like it. Right, I just put the perfect squares together. So I can just split these into two pieces, one with perfect squares and one without. Right, and I put the C6 first just because I had the perfect squares here first, so I might as well have the perfect squares here first. You don't have to do that. I just lined them up that way to make it nice. Okay, and so you split these apart, into, right, each one into 2 square roots. And then the first one on each of those simplifies. 2a times the square root of 15a over c cubed times square root of c. And then that simplifies to 2a, well, I just rewrote it as 2a over c cubed times, I just put the 2 square roots together again and the 2 non-square roots together. So 2a over c cubed times the square root of the quantity 15a over c. Now, either one of these last two is perfectly acceptable for answers. I think this one would be maybe a little more common than this one, but they're both perfectly fine.